Hello class, in this video I wanted to look at the general derivatives of exponentials. Sorry for having to cancel class at the last minute. My nose has been on fire for a good couple days and hopefully it is just allergies, but whatever it is, I haven't been feeling very well and just need to take a little bit of time off. But nonetheless, we can continue with class since we are a little behind with our schedule. Anyways, quick recap. In the past few classes, we've talked about the derivatives of exponential and logarithmic functions base e, which, again, I've gone on and on about. But if you recall, the derivative of e to the x, the natural based exponential function, is exactly itself. And a very important fact, which we talked about exponential growth and decay, and why that is relevant in the last couple classes. And also we looked at the derivative of the natural log function, which is just 1 divided by x, which we did implicitly on Monday. But we will be using those in the next couple videos to look at what if we have a log base 3 or a log base 10 or 10 to the x or a function such as that. How would we find a derivative from there? So let's start by considering 2 to the x, and it says use the definition of the derivative to find f prime. Now there's another easier way to do it, but let's just go ahead and look at what would happen if we were to approach it using the definition. So as we know, the definition of the derivative, what a derivative really is the limit as h approaches 0 of f of x plus h minus f of x over h. It's the limit of the slope of the secant line as the 2 points get closer and closer together. Or at the end of the day, we need to figure out, okay, what is the limit of this algebraic expression? And so for f of x is equal to 2 to the x, what we need to know is, well, what is f of x plus h? That would be 2 raised to the x plus h, because I'm going to, plug in x plus h into f of x. And similarly to how we did with e to the x a few classes ago, property of exponents is that if we have addition in the exponent, that is equal to 2 to the x times 2 to the h. Because if we have a certain number of 2's multiplied by another number of 2's, so say we have x2's multiplied by h2's, what that adds up to is a total of x plus h2's, right? Because that's what that means. 2 to the x plus h means I have that many 2's in succession, and this means the exact same thing. But this is helpful because, f of x plus h, if we plug that into our difference quotient, obviously if we want to solve the derivative, we need to know what that is, but we'd have 2 to the x times 2 to the h minus the original f of x all divided by h. So substituting in f of x plus h and f of x, what we'd have is the limit as h approaches 0 of this expression should be the derivative of 2 to the x. And similarly to e to the x and basically any exponential function, what you'll notice is that 2 to the x is a common factor in the numerator. And because that's a common factor, we could factor that through. And also, since x does not have to do with h, that can be passed through the limit. And I'll go ahead and do this a little bit faster because we already saw a similar tactic with e when we were talking about its derivative. But what we'd be left with is 2 to the x multiplied by the limit as h approaches 0 of 2 to the h minus 1 over h. And remember, this minus 1 came through because as we factored out 2 to the x from this term, all we would be left with is 1. And then this raises the question, okay, what is the limit of 2 to the h minus 1 over h? This is a very specific limit that, as a math professor, I would recognize this just because I've seen it so many times. But in general, if you wanted to know, okay, what is a limit, you could always take a numerical, graphical, algebraic approach. All the different things we've talked about. Now, we haven't really discussed an algebraic approach to finding such a limit. Because it's a little bit too difficult, but let's go ahead and do it numerically. And if I want to know that what's going on with a limit as it approaches 0, I could plug in, say, 0.01 or something very, very arbitrarily small into that. So I'll go ahead and use parentheses, 2 to the 0.01 minus 1 divided by 0.01. So I'm just substituting in 0.01 for h, which is not equal to the limit, but it's a way of approximating its value. And this would give us a value of about 0.696. And again, one of the limitations of the numerical, of solving limits numerically, is that it's not precise and we don't really necessarily know exactly what this is. So we could get a little closer. We could say, well, what about this limit if we were to plug in, say, 0.001 or something like that as well. So let's go ahead and try adding another 0 here to getting closer and closer to 0, because that's always what a limit is arbitrarily close to the specified value. And we see we're getting closer and closer to the value of about 0.693. And at the end of the day, again, we wouldn't really necessarily recognize what this number is, but it turns out that the limit of this very specific structure is always equal to the natural log of the base of the exponential. So say this were a 3 or a 4 or a 5, it would just change the natural log of that number. And so let's just go ahead and test out, well, what is the natural log of 2 in this case? Notice it's about 0.693, similar to the value that we obtained when we plugged in 0.001 into this expression. But this is a fact of this particular limit, which I've put on your lecture notes, which is not something I'd expect you to memorize. But basically, my point here is that this whole thing has a limit of the natural log of 2. So what we end up with is the derivative of our 2 to the x power, which is 2 to the x multiplied by the natural log of 2. And there we have it. And what I was saying similarly is, say we were dealing with an exponential function of a different base, it'd be the exact same pattern. So literally by definition, this is what we're looking at as the derivative of another exponential function. Now, I mentioned there's an easier way to show this, and that's what I wanted to show you guys how to do next, is by using the chain rule instead. And since we've already covered the chain rule quite a few times, we're good to go in this, and actually just ignore this in the notes. We don't need to actually use implicit differentiation to do this. But basically, this uses a different tactic. It says let f of x be equal to a to the x, basically a generally based exponential with anything. So 2 to the x, 5 to the x, 10 to the x, even e to the x, but whatever it is. And then what it says is on the lecture notes is, remember that a raised to the log ax is equal to x. So this cancellation property we reviewed a couple classes ago. I think this was on a different online lecture. But because log base a and a to the x are inverses, they exhibit particular cancellation properties. These were on our packet when we were solving equations, but these two properties right here, basically it's making use of this, and this is a fairly common strategy in some levels of calculus to do various things. For our class, we're not really going to be needing to know this tactic very often, but at the end of the day, this also implies that that cancellation property holds for any exponential composition if you're composing an exponential with a logarithm. And again, because they're inverses, they cancel each other. But e to the ln x works in the exact same way, because e is base e, so is the natural log. And basically, if I'm plugging in e into this formula, I would get e to the log e x, and that's why e to the ln x is equal to x. So sort of summarizing, if you're like, okay, why do I care about this random algebraic fact that when I take e raised to the ln x, it cancels? But basically, if we're looking at a to the x, we could replace the number a with e to the ln. And so, essentially we could put this whole thing, sorry, I actually misspoke slightly. Imagine that a to the x is x in this equation. We could put it into an e to the ln x. So looking at this, basically I'm replacing f of x equal a to the x with e to the ln a to the x. Because again, how I'm imagining it is e to the ln, that's meaningless. That all adds up to 1. So what I have is a to the x, it's equivalent due to those cancellation properties. So if you're like, okay, well, why would I put my a to the x function, to which we want to know the derivative of, into an e raised to the ln as we did? It's because logarithms have a very specific property. We've been reviewing a few of these log laws as we need to, but what we often call log law number 3, I wanted to revisit as well, is if you have a logarithm of any base to any number, let's just call it a, and let's say that's raised to the c power. Basically, if there's a power, technically it needs to be within the logarithm like this. Then that power will drop into the front of the logarithm. And that's often referred to as property number 3. But essentially, how I remember it is if I have an exponent inside of my logarithm on the interior of, say, x squared or something like that, it will change as a multiplier on the outside of the logarithm. And if you're asking yourself, well, why? Well, there are reasons why all those log laws are true. Don't want to get into that can of worms right now, but the log laws are very helpful, and that's how logarithms, they always work in that particular way. So anyways, if we're looking at the exponent, we have e raised to the ln ax. Well, x is an exponent within that expression. So by log law number 3, we could drop the x in front like this. So it'd have e raised to the x ln a, because that was an exponent on the logarithm. So I could drop that x from here into the front. And why that's helpful is, well, notice that my function, I've taken a base a function and I've rewritten it using e. And the reason why this is helpful is because we already know the derivative of e to the x. It's exactly itself. What we don't know is what's the general derivative of a to the x. And my point is, you can take any based exponential and you can change it to e using this property. And you know, essentially at the end of the day, there's not a huge difference between exponential functions of base e and any other base, which kind of, as we got into with e is sort of that special number with a lot of special properties. You can kind of all morph them into each other, contextually speaking, due to this particular algebraic fact. But anyways, what we want to know is the derivative. So my point is, we could find the derivative of this using the chain rule, because again, what we have is we have an inside and an outside. So like on the inside we have x ln a, and on the outside we have e. And so if we're going to do a derivative, we need to take the derivative of the outside. So derivative of e to the x is e to the x. So since I have e to the x ln a, we're going to leave everything alone, leave the inside alone as you take the derivative of the outside. So derivative of e to the x, nothing changes. It's exactly the same. But as we know, with the chain rule, I have to multiply by the derivative of the inside. That's the chain rule, right? Take the derivative of the outside, leave the inside alone, then multiply by the derivative of the inside. That is the chain rule. And I'll do it in red to be consistent with how I've always done it. But the derivative of the inside x ln a, well, it's just x times ln a is a constant. It's a value of a number, right? A is not a variable in this context. We're pretending it's 2, 3, or any number. X is the variable that we care about. But basically, I'm just imagining this is like a number times x, so like 3x. And the derivative of x is 1, and multiplied by a constant will not affect it. So the derivative of x ln a is just ln of a, because the derivative of x is just 1 when it's all by itself. And so what we're left with is, let me go ahead and switch back to the other ink. But we get e to the x ln a times ln a. Just like when we were taking derivatives of exponentials and talking about uninhibited growth, right? This is kind of like our rate of growth of our exponential. That's a natural log of the base a. Sort of summarizing this here is the difference between a to the x and e to the x is there's a growth rate that you need to tack onto there, the natural log of a. And when we take the derivative of e to the x, if there's a coefficient on it, we need to multiply by the coefficient, as we've been looking at with our derivatives in the past few classes. And so that's another way to make sense of that. But also another way that I could write this, because this is kind of getting a little bit more complicated of an expression, is really e to the x ln a. That's just equal to a to the x to begin with. Because if you think about all the steps we did to get here, I could put the x back, and then I could cancel out the ELN, and that would just leave me with a to the x. But that thing out here, this is just a to the x multiplied by the natural log of a. And what we have is our general derivative of any exponential function to any base. And I wanted to mention, notice this is the exact same thing we got in the previous thing. We got 2 to the x ln 2 as the derivative of 2 to the x. But what I was trying to show in this example is there's actually an easier way to go about it by using the chain rule. And we can show that this is true for any based exponential. And the last thing I wanted to just point out to you guys is, even if we were talking about e to the x, it still actually fits this formula, because if we were to plug in e for a, we'd have that the f of x equal e to the x. Our derivative would be e to the x times the natural log of e. And remember that e to the x, its derivative, is the only function whose derivative is exactly itself. Notice that that actually fits with this more generalized formula because the natural log of e is 1, right? Because a logarithm, when the base matches the exponent, it's always 1 by also general property of how logarithms work. Anyways, in the next video, let's practice a few examples of solving derivatives using these rules.